In question number 7, a ray of light is incident on the face of an equilateral prism of refractive index √2 in such a way that after first refraction, ray becomes parallel to the base of prism. Find the value of angle of incidence in degrees. So let's analyze the situation. Suppose this is an equilateral prism. So the prism angle is A, which is 60 degree. So the ray incident is something like this. This is normal, and after the first refraction, the ray becomes parallel to the base of the prism. It means it is the condition of minimum deviation. So we can write mu is equal to sine I. So sine I can be written as A plus delta minimum, that is minimum deviation, by 2 divided by sine R. So the value of R is A by 2 in the condition of minimum deviation. And this mu is given in the question as √2. Value of A is 60 degree. So if I solve this, the value of delta M comes out to be 30 degree. So the value of I, that is the angle of incidence, is A plus delta M by 2. So 60 plus 30 by 2. This is in degree. So it comes out to be 45 degree. So the correct answer for question number 7 is 45. Let's move to question number 8. In question number 8, n0 number of nuclei are taken at t equal to 0 of a radioactive element. At t1 equal to t0 second, number of nuclei are n1, and at t2 is equal to t0 plus 20 second, number of undecayed nuclei left are n1 by 2. If at t3 is equal to t0 plus x second, number of undecayed nuclei left are n1 by 8, then we have to find out the value of x. So let's analyze the situation. The number of nuclei at time t1 is n1. Here the time is t0. At time t0 plus 20 second, the number of undecayed nuclei left are n1 by 2. So from here we can say that the t half of this process is 20 seconds. Now we have to find out what is the value of x when the number of undecayed nuclei left are n1 by 8. So in the next t half interval, the number of undecayed nuclei left are 1 by 2 of n1 by 2, and here the time would be t0 plus 20 plus 20, and in the further 20 seconds, the number of undecayed nuclei left are 1 by 2 of n1 by 4. So this is at time t0 plus 20 plus 20 plus 20. So the number of undecayed nuclei left at time t0 plus x is n1 by 8. So on comparison, the value of x comes out to be 60. So the correct answer for question number 8 is 60. Let's move to question number 9. In question number 9, consider the shown circuit having 3 identical inductor, a resistor and a battery of 9 volts. Value of I0 in a steady state will be equal to. So I0 is the current through this inductor branch. So we know that in the case of a steady state, the inductor will behave like a conducting wire. So in that situation, the current through the battery I can be written as I is equal to E by R. So the value of E is 9, R is 1 by 10, is equal to 90 ampere. So now this current get distributed at this junction. Let the current in this branch is I1 and the current in this branch is I2. So we know that the induced EMF across these two branches will remain same. So L1 di1 by dt is equal to L2 di2 by dt, and on further integration we will get L1 I1 is equal to L2 I2. So we know that I is inversely proportional to L. So the current I1 can be written as I1 is equal to 2L divided by 3L into 90 ampere. So on solving, it comes out to be 60 ampere. So the correct answer for question number 9 is 60. Let's move to question number 10. In question number 10, Consider a thin uniform annular disc of mass 4 kg having inner and outer radius 3 meter and 4 meter respectively. A point mass m equal to 2 kg is taken from point P to infinity so that at infinity it has kinetic energy of 20 joule. If work done by external agent in this process is given by this expression, then we have to find out the value of n. So from work energy theorem, we know that the work done by external agent is equal to change in kinetic energy of system plus change in potential energy of system. So in order to find the potential energy, we have to find out what is the change in gravitational potential. So that is equal to final gravitational potential is 0 minus of gravitational potential at the initial state. So gravitational potential at the initial state can be written in this way. Suppose if I consider a ring at a distance x and another ring at a distance x plus dx from the center, then the mass of this considered element dm can be written as capital M divided by pi into 16 minus pi into 9 into the area of this segment. So that is 2 pi x dx. So dm can be written as m divided by 7 pi into 2 pi x into dx. So this is dm. So the gravitational potential due to this dm at this point P can be written as dm g into can be written as minus capital G into dm divided by r. So the value of r is this, and this can be written as under root of x square plus 4 square, that is 16. So if I take the integration from x is equal to 3 to 4, then this will give the value of the gravitational potential at point P in the initial state. So on solving, it comes out to be 2 by 7 g into m into 4 root 2 minus 5. So if I substitute the data, then this is equal to change in kinetic energies. Final kinetic energy is 20 joule, initially 0. So 20 minus 0 plus change in potential energy, that is mass into delta V. So this can be written as 2 by 7 g small m capital M into 4 root 2 minus 5. So if I substitute the value of small m and capital M, that is 2 and 4, so this product would be 16 by 7 g into 4 root 2 minus 5. So if I compare this with the given expression, then the value of n comes out to be 4 or 0.4. So the correct answer for question number 10 is 0.4. Let's move to question number 11. In question number 11, a point mass m is attached at point A on a uniform circular disc of equal mass m and radius r, which can rotate freely in vertical plane about an axis PQ as shown. If disc is released from the position when point mass m at the highest point, then hinge reaction when the center of mass of complete rigid body is at lowest point is given by this expression. So we have to find out the value of n. So at the instant when the center of mass of the complete rigid body is at lowest point, then the situation is something like this. And at that moment, the center of mass of the system is at this position, which is initially at this point. So if I calculate this distance, the center of mass of these 2 points would be at the midpoint, that is at a distance r by 2. So this r by 2 plus r by 4, this is 3r by 4. So this separation is at 3r by 4. This is the position of the center of mass of the complete system. Now at this moment the angular velocity of the disk is omega. So we can apply the principle of conservation of mechanical energy, that is the loss in potential energy is equal to gain in kinetic energy. So the loss in potential energy can be written as mg into 2 times. If I consider this as my gravitational potential 0 reference frame, then this separation would be r plus r by 4, that is 5r by 4. So 2 times 5r by 4 plus, if I write of this mass m, then mg into 2 times r by 4. So that is the loss in gravitational potential energy, that is equal to gain in kinetic energy. So gain in kinetic energy is rotational kinetic energy half into I. So I about this axis of the complete system we have to write. So the moment of inertia of this disk about this axis is mr square by 4 plus about this axis we have to apply parallel axis theorem. So m into r by 4 whole square, this is of disk about this given axis, plus moment of inertia of the point mass about this axis can be written as m into 5r by 4 whole square into omega square. So if I solve this, the value of omega square comes out to be 16g by 5r. So at this moment, if I write the hinge reaction, then 2mg mass is acting on this in this direction. So I can write the hinge reaction is upward, vertically upward. So force due to hinge in vertical direction minus 2mg is equal to mass of the complete system, that is 2m into AC. So AC is omega square r. So the value of omega square is 16g by 5r into the value of r is 3r by 4. So if I solve this, the hinge reaction comes out to be 34 by 5 mg. So on comparison, the value of n is 34. So the correct answer for question number 11 is 34. Let's move to question number 12. In question number 12, a ring of radius r is equal to 2 meter is rotated with constant angular velocity omega about an axis passing through O. A uniform magnetic field B is equal to 2 Tesla exists perpendicular to the plane of ring. Find induced EMF in volts between point O and A. So we have to find out induced EMF between these 2 points. So we know that induced EMF delta E is given by V cross B dot dl vector. So if I integrate this, then the induced EMF between point O, then induced EMF between point A and O is given by E is equal to half into B into omega into L effective between point A and O square. So the L effective separation between these two is root 2r. So this can be written as half into B omega into root 2r square. So that is 2r square. So if I substitute the data, the value of B is 2, the value of omega is 4, and the value of r is 2, its square is 4. So this comes out to be 32 volts. So the correct answer for question number 12 is 32. Let's move to question number 13. In question number 13, the effective resistance between points P and Q as shown in figure is 40 by n ohm. We have to find the value of n. So if we see the symmetry, this junction and this junction are connected by the same resistors. So whatever is the current, so let X, so if X is the current in this branch, Y is the current in this branch, and again due to symmetry of this branch and this branch, X is the current in this branch, then this current will go in this way and this junction is of no use. Similarly, the current in this move in this direction and the current in this branch will move in this direction. So we can replace this, so we can remove this 8 ohm resistor and this 8 ohm resistor. In that situation, These 8 and 8 are in series, so the resultant is 16, and this also, and the resultant of this branch is also 16. So 16 and 16 are in parallel, so the resultant is 8, and this 8 is in parallel with this 4. So the equivalent of these three branches comes out to be 8 into 4 divided by 12. So it comes out to be 8 by 3 ohm. Now this 8 by 3 ohm is in parallel with this 10 ohm. So R equivalent about point P and Q would be 8 by 3 into 10 divided by 8 by 3 plus 10. So on further solving, it comes out to be 40 by 19 ohm. So on comparison, the value of N comes out to be 90. Let's move to question number 14. In question number 14, if 2 moles of an ideal monatomic gas is heated through a process for which Pt is equal to constant, if increase in the temperature of the gas is 5 by R Kelvin, then heat supplied to the gas in joule is. So if I see the process equation is Pt is equal to constant, or T can be replaced as P into V is equal to constant, because the gas is ideal in nature, or I can write P into V raised to the power half is equal to constant. So if I compare with the polytropic process, PV raised to the power x is equal to constant, then the value of x comes out to be half. So in that case, the molar heat capacity is given by Cv plus R divided by 1 minus x. So the value of Cv for the monatomic gas is 3R by 2 plus R divided by 1 minus half, that is half, so it comes out to be 2. So on solving, it comes out to be 7R by 2. So the heat supplied can be written as Nc dt. So the value of N is 2, the value of C is 7R by 2, and the value of dt is 5 by R. So on solving, it comes out to be 35 joule. So the correct answer for question number 14 is 35. Let's move to question number 15.